Oh, hi everyone. According to statistical analysis conducted by Dr. Samuel Arbesman of Harvard, that's the UCF of the Northeast, empires from 3000 BC to 600 AD, whatever those things are, 300 to there, they last an average of 22 decades. That apparently that's how it goes. I guess there's stuff about nothing lasts forever, even cold November rain. Apparently the same holds true for empires. This problem I just Googled on my other computer. That doesn't matter, but I did 100 divided by 10. Like, I literally Googled that. That's where my arithmetic skills are. Now consider why I did that. Not, if, say it was something like a reasonable division problem. Think about that for a moment. And I'll continue to feel bad that I did it. But then probably forget just as easily. Why am I messing around with that stuff? Keep thinking about that, and I'll keep trying to figure out how to do this problem. What's interesting about this is I don't know. I think it's pretty interesting. This is real. 22 decades is how many years? Or 100 years is how many decades? Right? So why I took 100 and divided by 10 is that gives me 100 years is it turns out, according to Google, this is 10 decades. So there you go. That's why Harvard is the UCF of the Great Northwest, is because statistics instructors, I'm not representative, but I have to Google 100 divided by 10, and that's 10 decades. We have a Poisson distribution. At least we can apply the Poisson model here. Okay? The only trap situation here is that you've got to convert either to years or decades. Either way, you'll get the same answer. Alright? The Poisson random variable, you could use the table. If the table, I think if you look through your tables, I don't know if it goes up to 22. It probably, well, it does. No, it doesn't. Does it? No. We're looking at these tables are a lot of fun. A lot of fun at parties. Pull out your Poisson table. Right, if somebody's using the bathroom every 3 people are using it per a 10-minute interval, what's the probability that 5 people use it? You might have something to consider. Anyway, I'm just going to use the formula, the binomial, not the binomial, the Poisson mass function formula, because it's a lot of fun. And people like it, I like it, and it's really cool. One cool thing about the Poisson distribution is it's an example, once again, in history where the person that actually did the most doesn't even get credit. I can't even remember the gentleman's name. It's like Berkowitz or something like that. No, he was a serial killer. Not David Berkowitz, but I don't know. It's like when countries were called Prussia, there was a P in front of Russia, and the story is that this guy was trying to figure out how many of his soldiers were getting killed by like friendly horse fire. So like the horses would like buck and kill their own men, and for some reason this was a good time to expand upon the binomial distribution, and from there a lot of work was done to get the Poisson distribution. And Simeon Poisson came along and said, "Thank you, we'll name it after me." I wasn't delaying there. I just think that for this, because that is actually a cool story. All right, denominator, is x factorial, and then in the numerator, what goes there? I know there's an e somewhere in there. All right, where's that e? Actually, I can't remember it. That's really, it's pretty good. It's pretty good. One thing I want to point out here is that I like to use this notation for it, but oftentimes you'll just see that written as the mean, because that's the mean number of occurrences, independent occurrences, in what's called a stochastic process. And you can actually model the time between those hits or events using, in our book, it's just called the exponential distribution. Anyway, lambda is the rate raised to the x power, and then we have e equals not mc squared, but then we have e to the lambda power. Okay, so on average, how often does blah 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 happen? This says empires last. That's the situation here. That's what our random variable would represent. Let's see, what would x equal here? Like the random variable thing we're modeling. Number of what? I'm just use number of decades. You could use number of years if you want, but I'm sticking with number of decades. Empire lasts. So, good Star Wars reference there. All right, we're going to take this, and next to the equal sign, we're going to draw a line. And then in denominator, I'm going to put the value of the random variable that I'm interested in. That was what I went through. I have in the red that I Googled to find out was 10. 10 factorial. 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2. And then in the numerator, well, whoa, wait a second. On average, they last 22 decades. So they're not all going to last exactly 22 decades. It's a random variable. Okay, it's subject to variation, dispersion, fluctuation, mutation, change, variance, deviation. All right, let's wrap this thing up. 22 decades is the norm. And I'm going to raise that to the 10th power. There's we got an x here, and we got an x here. All right, and then we have the base of the natural logarithm. Put a factorial there, and I'm going to raise this to the lambda power. And then from there, you can go ahead, and now's a good time to use Google. That equals, I think you can just talk to Google now, but I'm still going to plug it in. 22 caret 10. I like this because you don't need any parentheses. E 22 fraction 10 exclamation point. Let's go. Come on, work. Come on, work. I don't think I did it right. 22 to the 10th. That's right. E to the 20. Yeah, that's right. Divided by 10 factorial. Feels like too small a number. So this will have to be deleted or changed later on. But for now, we'll leave it as is, and we'll come back to this in a little while. This is how you don't do it, apparently. Stop.